At cruising altitude, surrounded by an atmosphere so thin it borders on vacuum, a modern jet appears serene, stable, untouchable. Its wings stretch wide with mathematical elegance, its fuselage pressurized into a perfect cylinder, every rivet and composite panel calculated to tolerate forces far beyond those of ordinary machines. This aircraft is not merely a vehicle, it is a declaration of confidence. Lift is produced smoothly, predictably, governed by equations refined over more than a century. Angle of attack, airflow velocity, pressure differentials. Every parameter is monitored, modeled, and fed into layers of redundant computers. From the outside, the system looks invincible. Engineers speak of safety margins, load envelopes, and certified limits with quiet assurance. This machine, they say, cannot be surprised. The wing itself is a triumph of modern aerospace architecture. Beneath its smooth skin lies a complex skeleton of spars, ribs, and stringers, machined or molded to tolerances measured in fractions of a millimeter. High-strength aluminum alloys blend with carbon fiber reinforced polymers, each chosen for a precise balance of stiffness, fatigue resistance, and weight. The skin is not simply a covering. It is a load-bearing element, designed to share aerodynamic forces with the internal structure. When the aircraft flies, lift does not act gently. It bends the wing upward with thousands of tons of distributed force, twisting it subtly along its span. Yet the structure absorbs this stress, cycle after cycle, flight after flight, as if it were effortless. This confidence extends to the flight envelope itself. The stall, once a constant threat in early aviation, is now treated as a controlled, almost academic concept. Modern aircraft are equipped with sophisticated sensors measuring angle of attack, airspeed, and inertial motion hundreds of times per second. Flight control laws intervene long before the wing reaches its critical angle. Stick shakers warn, computers limit control inputs, automated systems nudge the aircraft back towards safety. In design reviews, the stall is discussed as a boundary condition, not a looming danger. The assumption is clear: the architecture will always protect the crew from crossing that line. But this confidence hides a subtle truth. The stall is not merely an aerodynamic event. It is a structural and material phenomenon as well. As angle of attack increases, airflow begins to separate from the wing's upper surface. Lift decreases, but drag and unsteady aerodynamic loads increase sharply. These loads do not act uniformly. They fluctuate, buffet, and migrate across the wing, introducing localized stresses that were never present in normal cruise. The structure responds elastically, but within that response lie microscopic concentrations of stress, tiny amplifications at fastener holes, composite ply interfaces, and bonded joints. On paper, they are insignificant. In reality, they are seeds. The first flaw is not dramatic. It is invisible, born at the intersection of design assumptions and physical reality. Perhaps the engineers assumed a certain airflow behavior at high angles of attack, validated by wind tunnel models that could not perfectly replicate full-scale turbulence. Perhaps they underestimated how thermal expansion would interact with aerodynamic heating during repeated climb cycles. Or perhaps the choice of material, lighter, more efficient, introduced a sensitivity to cyclic loading that was dismissed as acceptable. None of these decisions appear reckless in isolation. Together, they form a hidden vulnerability. Consider the wing skin near a critical structural joint. Each flight imposes a load cycle: pressurization, lift, vibration, relaxation. Metals respond to these cycles with fatigue, a slow accumulation of damage at the atomic level. Dislocations move, microvoids form, and grain boundaries weaken. In composites, resin microcracks appear between fibers, invisible to the naked eye, but very real to the structure. Under normal conditions, these processes are glacial. The aircraft is certified for tens of thousands of cycles with ample margin. But near the edge of the envelope, near the stall, the loading spectrum changes. Stress ranges widen. Frequencies shift. What was once benign becomes aggressive. This is the invisible degradation. Inside the wing, a crack begins as a whisper, a few microns long, emanating from a rivet hole or a bonded interface. Each time the aircraft approaches high angle of attack, each time it experiences buffet or control law intervention, that crack advances imperceptibly. Engineers call this crack propagation, governed by fracture mechanics equations that describe how stress intensity factors drive growth. The crack does not care about certification documents or confidence. It obeys physics alone. For years, nothing appears wrong. Inspections reveal no obvious damage. Non-destructive testing methods, ultrasound, eddy current, are calibrated to detect flaws of a certain size. This one is smaller. The aircraft continues to fly, accumulating cycles, accumulating damage. The stall remains theoretical, a condition rarely encountered in line operations. Yet the structure is being prepared, quietly, for a moment of truth. That moment arrives not as a single mistake, but as a convergence. Weather deteriorates. Airspeed margins shrink. Automation commands a pitch increase to maintain altitude. The angle of attack climbs toward its limit. The airflow over the wing becomes chaotic, separating and reattaching in violent patterns. Lift fluctuates, and with it, the bending moment at the wing root surges. The microscopic crack, now grown to a critical length, experiences a sudden spike in stress intensity. In fracture mechanics, this is the tipping point. Stable growth becomes unstable. The structure yields, not gradually, but catastrophically. A section of wing skin tears, releasing stored elastic energy in an instant. The load redistributes violently to neighboring components, which were never designed to carry it. They fail in rapid succession, like dominoes made of metal and composite. The wing loses stiffness, its aerodynamic shape distorts, and lift collapses asymmetrically. The aircraft enters a deep stall, one from which recovery is no longer a matter of control inputs. Physics has taken over. The aftermath is chaos measured in seconds. Sensors disagree. Warnings cascade. Control surfaces respond, but their effectiveness is compromised by the altered airflow and damaged structure. If the failure occurs at altitude, decompression may accompany it, the sudden roar of escaping air underscoring the violence of the event. If it occurs closer to the ground, there is no time. The aircraft descends, not as a controlled glide, but as a system unraveling faster than human cognition can follow. When the wreckage is examined, or when a fleet is grounded after a near miss discovered in a hangar, the illusion of invincibility collapses. Investigators begin the forensic process with almost ritual precision. Every fragment is cataloged. Fracture surfaces are examined under scanning electron microscopes, revealing telltale beach marks that map the history of crack growth. Metallurgists analyze alloy composition and grain structure. Composite specialists study delamination patterns. The story emerges not of a single failure, but of a chain of assumptions. The root cause is rarely simple. It may be traced to a design choice that underestimated high angle of attack loads, or to a certification regime that focused on aerodynamic stall behavior while overlooking structural consequences. It may involve maintenance procedures that failed to detect early damage, or operational practices that brought the aircraft repeatedly close to its limits. In many cases, it is a form of engineering hubris, the belief that automation and redundancy have conquered a fundamental aerodynamic boundary. The legacy of such failures is written into new regulations and new designs. Certification authorities mandate expanded fatigue testing that includes high angle of attack loading spectra. Engineers redesign critical joints, smoothing stress concentrations, thickening skins, changing fastener patterns. Sensors are added, algorithms refined, but with a renewed respect for the physical limits they monitor. The stall is redefined not just as an aerodynamic event, but as a structural one, a condition where airflow, materials, and time intersect with unforgiving precision. In the end, the lesson is stark. Modern aircraft are masterpieces of engineering, but they are not immune to the laws of physics. A stall is not merely a loss of lift. It is a stress test of every assumption embedded in metal and composite. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault. The investigation does not stop at the visible rupture. It never does. In aviation forensics, the obvious failure is treated as a symptom, not a cause. When engineers reconstruct the sequence leading into a stall-induced structural event, they rewind the clock thousands of flight hours. They analyze not just what broke, but why it was allowed to weaken in the first place. The data recorders reveal subtle patterns. Repeated approaches flown close to minimum speeds, automation compensating with incremental pitch commands, wings operating closer to their critical angle of attack more often than the designers originally envisioned. Each of these moments, insignificant on its own, contributed to a loading environment that quietly eroded structural margins. At high angles of attack, airflow over a wing becomes fundamentally unstable. This instability manifests as buffet, random, high-frequency pressure fluctuations that strike the wing skin like invisible hammer blows. In computational models, these loads are often averaged, smoothed into neat curves. In reality, they are chaotic. Pressure spikes migrate across the wing's surface, concentrating stress at specific locations. Rivet holes, fastener countersinks, and bonded joints experience micro-level stress intensification far above nominal values. The structure survives, but it remembers. This memory is encoded in the material itself. In aluminum alloys, cyclic loading causes persistent slip bands to form within individual grains. These microscopic features concentrate strain and eventually nucleate cracks. In composite structures, the process is different but no less insidious. Fibers remain intact, but the resin matrix between them begins to craze and crack. Layers debond, creating hidden delaminations that reduce stiffness without obvious external signs. Each high angle of attack event, each brush with the stall boundary, accelerates this degradation. Engineers once believed that these effects were negligible in modern aircraft. The logic was seductive. If automation prevents pilots from stalling the aircraft, then the structural consequences of a stall need not be fully explored. This assumption shaped design trade-offs. Weight savings were prioritized. Safety factors were trimmed, justified by the presence of flight envelope protection systems. The wing was optimized for cruise efficiency, not repeated exposure to near-stall conditions. On paper, the margins remained acceptable. In service, reality proved more complex. As the aircraft ages, the cumulative effect of these design choices becomes apparent. The crack that began as a microscopic flaw grows according to well-understood laws of fracture mechanics. Each cycle increases the crack length, which in turn increases the stress intensity at its tip. This positive feedback loop is merciless. The structure becomes progressively less tolerant of abnormal loads. A maneuver that was once safe now pushes the material closer to its fracture toughness limit. The danger lies in the nonlinearity of this process. Crack growth is slow, almost imperceptible, until it is not. For thousands of cycles, the crack advances by microns. Then, in a single event, it grows by millimeters. The transition from stable to unstable crack growth occurs without warning. There is no gradual degradation in handling qualities, no obvious sign to the crew. The aircraft feels normal until the instant it does not. When that instant arrives, the stall is no longer an abstract aerodynamic concept. It becomes a structural crisis. The loss of lift at high angle of attack is accompanied by a violent redistribution of loads. As airflow separates, pressure on the wing drops unevenly. One wing may stall before the other, introducing rolling moments that further stress the structure. Control surfaces deflect aggressively as the flight control system attempts to recover, adding torsional loads to an already compromised wing. The crack, now critically long, cannot withstand this assault. The fracture propagates at the speed of sound through the material. Engineers describe this as rapid fracture, a regime where inertia and energy release dominate. The wing skin tears open, exposing internal structure to the airstream. The sudden loss of stiffness allows the wing to twist beyond its design limits. Aerodynamic loads spike again, feeding back into the failure. In seconds, the structural integrity of the wing is compromised beyond recovery. The aftermath is studied with almost clinical detachment. Investigators trace fracture surfaces, noting the characteristic patterns that distinguish fatigue from overload. They identify the origin point of the crack, often at a feature so small it seems trivial: a machining mark, a slight misalignment, a microscopic void left over from manufacturing. This is where the narrative shifts from dramatic failure to uncomfortable introspection. The flaw was always there. The physics was always understood. What failed was the assumption that it would never matter. Regulators respond with sweeping changes. Certification standards are rewritten to require full-scale fatigue testing under expanded loading conditions, including repeated high-angle of attack scenarios. Designers are forced to confront the reality that automation does not eliminate physics, it merely delays its consequences. Wings are redesigned with smoother load paths, thicker skins, and reduced stress concentrations. Composite layups are modified to improve damage tolerance. Inspection regimes are enhanced, incorporating advanced non-destructive techniques capable of detecting smaller flaws earlier in their life. Yet, even as technology advances, the fundamental lesson remains unchanged. The stall represents a boundary not just of aerodynamics, but of engineering philosophy. It is where confidence meets reality, where mathematical models encounter the chaotic complexity of the physical world. Modern aircraft may be protected by layers of software and sensors, but beneath them lies a structure governed by immutable laws. Metals fatigue, composites crack, stress concentrates where designers least expect it. In the quiet of a hangar, with an aircraft grounded for inspection, the danger feels abstract. Engineers pore over data, debating millimeters and megapascals. But in flight, at altitude, near the edge of the envelope, these abstractions become brutally real. A stall is no longer a warning in a manual. It is a test of every decision made during design, manufacturing, and operation. The history of aviation is filled with moments like these, moments when confidence outpaced caution, when assumptions hardened into dogma. Each failure rewrites the rulebook, often at a terrible cost. And yet, the cycle continues. New materials, new algorithms, new architectures promise to finally tame the stall, to make it irrelevant. Experience suggests otherwise. The stall endures because it is not a flaw in design, but a reminder of limits. As investigators close their reports and fleets return to service with modifications and mandates, the aircraft once again takes to the sky, appearing as serene and invincible as ever. The wing flexes gracefully. The skin gleams. The systems hum with quiet authority. But embedded within that structure is a memory of failure, a record written in microcracks and revised regulations. It is a silent testament to the fact that in aviation, safety is never a finished achievement, only a continuous negotiation with physics. And that negotiation is never won outright. It is managed, respected, and occasionally relearned through catastrophe. The stall, lurking at the edge of performance, remains one of its most unforgiving teachers. In the controlled language of accident reports, this phase is often summarized with a single phrase: loss of structural margin. But that phrase conceals a complex and deeply unsettling reality. Structural margin is not a fixed quantity. It is not a number frozen in the design stage and preserved forever. It is a living buffer, constantly consumed by time, usage, environment, and assumptions. And nowhere is that margin eroded more aggressively than near the aerodynamic stall. As an aircraft repeatedly approaches high angles of attack, the wing enters a regime of unsteady aerodynamics. The airflow no longer follows smooth, predictable streamlines. Instead, it separates in patches, reattaches, then separates again. These oscillations generate dynamic pressure loads that excite the wing's natural vibration modes. Engineers call this aeroelastic coupling. The wing is not just producing lift, it is flexing, twisting, and vibrating in response to chaotic airflow. Each vibration cycle adds another microscopic insult to the material. From a structural standpoint, these vibrations are far more damaging than steady loads. Fatigue damage is driven not by maximum stress alone, but by stress range and repetition. A wing cruising at altitude experiences relatively constant loading. A wing operating near stall experiences rapidly fluctuating loads with high stress gradients. Rivet holes elongate by nanometers. Composite plies experience interlaminar shear. Adhesive bonds are stressed and peel rather than pure shear, a condition they tolerate poorly. None of this is visible. None of it triggers an alarm. Designers attempt to account for these effects using safety factors and fatigue spectra. But those spectra are only as good as the assumptions behind them. If the operational reality shifts, if automation routinely flies closer to stall margins to optimize fuel efficiency, or if pilots rely on envelope protection rather than raw aerodynamic cues, the loading environment changes. The aircraft begins to live a life its designers did not fully anticipate, and materials respond not to intentions, but to forces. One of the most dangerous aspects of stall-related structural degradation is its asymmetry. Wings are theoretically identical, but in practice, no two structures age the same way. Minor manufacturing differences, slight variations in material properties, or uneven exposure to moisture and temperature gradients can cause one wing to degrade faster than the other. Near stall, where lift margins are razor-thin, this asymmetry becomes critical. One wing may experience earlier airflow separation, producing uneven loads that twist the structure further out of alignment. The result is a feedback loop. Aerodynamic imbalance drives structural stress, which worsens aerodynamic imbalance. Flight control systems attempt to mask this behavior. They sense roll or yaw rates and command corrective inputs. But those corrections themselves impose additional loads. Spoilers deploy, ailerons deflect, control surfaces move rapidly to counteract asymmetry. Each movement introduces localized stress into hinges, actuators, and attachment points. The structure absorbs these loads as it always has. But now, it does so with diminished reserves. At this stage, the aircraft is no longer simply approaching a stall. It is approaching a systemic failure threshold. The difference between recovery and catastrophe is measured in fractions of a second in fractions of a degree of angle of attack. If the crack within the wing skin or spar has reached its critical length, the next load spike will not merely extend it, it will unleash it. When that happens, the transition is instantaneous. The crack propagates unstably, driven by the release of stored elastic energy in the bent wing. Fracture mechanics describes this moment with chilling precision. The energy available for crack growth exceeds the material's fracture toughness. There is no equilibrium solution. The structure fails until the energy is dissipated, which may require tearing through large sections of skin, spar, or rib. The aerodynamic consequences are immediate and severe. The wing's load-carrying capability collapses locally, forcing lift to redistribute abruptly. This redistribution is not smooth. It generates shock-like load transfers to adjacent structure, which may already be weakened. In some cases, the failure propagates span-wise, peeling the wing skin back under aerodynamic suction. In others, the wing twists violently, exceeding control surface authority and inducing a deep, unrecoverable stall. From the cockpit, the event is bewildering. Instrument indications lag reality. Airspeed readings fluctuate wildly due to disturbed airflow around the pitot probes. Angle of attack sensors may saturate or provide conflicting data. The flight control computers, receiving inconsistent inputs, revert to degraded modes or disengage protections entirely. The crew is left with an aircraft that no longer behaves like the one they were trained to fly. This is where the concept of hubris becomes unavoidable. Not the arrogance of individuals, but of systems. The belief that complexity can fully tame nature. The belief that if enough sensors, algorithms, and redundancies are added, fundamental aerodynamic and structural limits can be rendered irrelevant. The stall exposes the fragility of that belief. It strips away layers of abstraction and reveals a simple truth. When lift collapses and structure fails, there is no software patch. In the aftermath, whether it ends in impact or a narrowly avoided disaster, the industry turns inward. Investigators reconstruct the loading history of the aircraft with forensic rigor. They simulate high angle of attack events in wind tunnels and computational models, now informed by real-world data. They discover that certain structural details experience stress ranges far higher than predicted, that certain materials exhibited fatigue behavior more aggressive than expected under combined aerodynamic and thermal loading, that inspection intervals were calibrated to detect cracks after they had already passed critical thresholds. These findings are deeply uncomfortable because they challenge the narrative of continuous progress. They force engineers to admit that optimization has consequences. Lighter structures, thinner skins, and tighter margins improve efficiency but reduce tolerance to the unexpected. Automation that prevents pilots from feeling the onset of stall also deprives the structure of gentler handling. The aircraft is protected from one kind of error, only to be exposed to another. The response is not to abandon technology, but to reframe humility as a design requirement. New aircraft are subjected to more punishing fatigue tests, cycling through load cases that deliberately include repeated near-stall conditions. Structural health monitoring systems are embedded into wings, using strain gauges and acoustic sensors to listen for the earliest signs of damage. Certification authorities demand proof not just of aerodynamic recovery from stall, but of structural survivability in its vicinity. Yet, even as these measures are implemented, the stall remains what it has always been, a boundary condition where multiple disciplines collide. Aerodynamics, materials science, structural mechanics, human factors, and software engineering all converge here. A weakness in any one of them can tip the balance. That is why stall-related failures are so instructive and so unforgiving. They remind the industry that safety margins are not static. They are consumed quietly, invisibly, flight by flight. They remind engineers that every design assumption carries risk, especially when it relies on perfect behavior from imperfect systems. And they remind everyone involved that the sky is not forgiving of complacency. As the aircraft of the future takes shape, more efficient, more automated, more complex, the stall will continue to lurk at the edge of performance. It will test not just wings and skins, but philosophies. Whether those philosophies are grounded in respect for physical limits, or in confidence that technology alone can transcend them, will determine how often the lessons of the past must be relearned. By the time the failure becomes visible to instruments, it is already complete at the microscopic level. The decisive moment does not begin with alarms or warnings. It begins inside the material itself, at a scale measured in microns, where the accumulated damage reaches a point of no return. In fracture mechanics, this threshold is defined with brutal clarity, the critical crack length. Once exceeded, the structure is no longer governed by gradual fatigue loss, but by unstable energy release. The wing is no longer a resilient beam. It becomes a loaded spring snapping free. As the aircraft approaches or enters a stall, aerodynamic forces change character. Lift no longer increases smoothly with angle of attack. Instead, it collapses unevenly, creating sharp gradients in pressure across the wing surface. These gradients translate directly into structural loads. Bending moments spike at the wing root. Torsional loads surge as airflow separates asymmetrically. What makes this moment uniquely destructive is not the magnitude of the loads alone, but their rate of change. Structures are designed to carry high loads if they are applied gradually. Near stall, loads are applied violently, with little warning. The cracked region experiences this surge first. Stress intensity at the crack tip increases beyond the material's fracture toughness. Atomic bonds fail in rapid succession, releasing stored elastic energy faster than it can be dissipated. The crack accelerates, no longer creeping but racing through the material. Engineers describe this as brittle-like behavior, even in materials that are nominally ductile. At high strain rates, there is no time for plastic deformation to blunt the crack tip. The material behaves as if it were glass. In a metallic wing skin, the crack tears through rivet lines and stringer attachments, severing load paths that were never meant to be interrupted. In composite structures, the failure manifests differently, but with equal violence. Delaminations unzip between plies, fibers snap under tension, and entire sections of laminate lose coherence. The wing skin, once a smooth aerodynamic surface, begins to deform under aerodynamic suction, ballooning outward or collapsing inward depending on local pressure fields. This deformation feeds back into the aerodynamics almost instantly. The wing's carefully designed airfoil shape is distorted, destroying what little lift remains. Flow separation spreads rapidly, deepening the stall. Control surfaces lose effectiveness as they operate in fully separated flow. The flight control system commands maximum corrective deflections, but those commands now act on a structure that can no longer transmit loads as intended. Hinges and actuators are subjected to forces far beyond their design envelope. Within seconds, the failure propagates beyond its point of origin. Load redistribution transfers stress to adjacent ribs and spars, which may already be compromised by fatigue. Secondary failures follow. A spar cap fractures. A rib buckles. The wing twists violently, altering the angle of attack even further and locking the aircraft into a deep stall. This is no longer a recoverable aerodynamic condition. It is a structural cascade. From the cockpit, the experience is disorienting and terrifyingly fast. The aircraft may roll abruptly as one wing loses lift more completely than the other. Pitch control becomes erratic. Airspeed indications fluctuate as disturbed airflow washes over sensors. Warnings overlap, some triggered by genuine failures, others by sensor disagreement. The human brain, trained to diagnose failures over seconds, is overwhelmed by events unfolding in fractions of a second. There is a cruel irony in this moment. Modern aircraft are designed to protect crews from stalls through automation, envelope protection, and layered warnings. But when structural failure accompanies a stall, those protections become irrelevant. The system was designed under the assumption that the wing would remain intact. Once that assumption is violated, every dependent system collapses conceptually, even if it remains electrically functional. If the failure occurs at high altitude, decompression may accompany the structural rupture. The sudden loss of pressurization introduces another violent transient, subjecting the fuselage and remaining structure to rapid pressure equalization. If it occurs at lower altitude, the margin for recovery is measured in hundreds of feet, not thousands. In either case, the outcome is determined less by pilot action than by the physics already in motion. When impact occurs, it is often misinterpreted in public narratives as a loss of control or a pilot error. But forensic analysis tells a different story. Investigators find fracture surfaces showing classic fatigue striations leading into regions of rapid overload. They reconstruct the final seconds and discover that control inputs were present, logical, and timely. The aircraft did not fail because it was mishandled. It failed because its structure had been living on borrowed time. In cases where catastrophe is narrowly avoided, the discovery of damage in a hangar sends shockwaves through the industry. A routine inspection reveals a crack far larger than expected, sometimes extending through multiple structural elements. Engineers realize that the next flight, or the next high angle of attack event, could have triggered catastrophic failure. Fleets are grounded. Flight schedules collapse. Confidence evaporates overnight. The immediate aftermath is dominated by containment. Operators ground affected aircraft. Regulators issue airworthiness directives. Manufacturers assemble crisis teams. But beneath the operational urgency lies a deeper reckoning. How did a structure certified to withstand decades of service reach such a precarious state without detection? How did design margins erode so completely without triggering alarms? The answers are uncomfortable. Fatigue testing during certification often focuses on representative load spectra derived from historical operations. But as flight control systems evolve, operational behavior changes. Aircraft fly smoother profiles, but closer to performance limits. Automation trims away human variability, but in doing so, it concentrates loads into narrower regimes. What was once an occasional excursion near stall becomes a routine operating point. The structure is exposed to a different kind of wear, one that was not fully anticipated. Inspection regimes, too, are revealed as imperfect. Non-destructive testing methods are powerful, but they rely on assumptions about where damage is likely to occur and how fast it will grow. When cracks initiate in unexpected locations, or when growth rates accelerate due to combined aerodynamic and thermal effects, inspections can miss them until they are dangerously large. The aircraft, outwardly pristine, becomes structurally fragile. This is where the narrative of hubris crystallizes. Not arrogance in the sense of negligence, but confidence hardened into certainty. The belief that modern analysis tools, computational models, and automation have closed the gap between prediction and reality. The stall exposes the limits of that belief. It reveals that even the most advanced simulations cannot capture every interaction between airflow, structure, and time. It reminds engineers that materials do not read certification documents. In the forensic laboratories, investigators measure, catalog, and analyze, but the implications extend far beyond a single airframe. Every similar aircraft becomes suspect. Every design assumption is revisited. Engineers re-examine stress concentration factors, revisit composite damage tolerance, and reassess the coupling between aerodynamic loads and structural response near stall. What emerges is not a single fix, but a series of corrections, each addressing a piece of a much larger puzzle. The stall, once treated as an aerodynamic boundary safely managed by software, is redefined as a multidisciplinary hazard. It is no longer enough to demonstrate that an aircraft can recover aerodynamically from a stall. It must also be shown that its structure can endure repeated proximity to that boundary without accumulating hidden damage. This realization reshapes design philosophy. Future wings are built with increased damage tolerance, even at the cost of weight. Stress concentrations are smoothed aggressively. Load paths are made more redundant. Composite layups are designed to fail gradually rather than catastrophically. Structural health monitoring systems are embedded, turning wings into self-reporting structures that reveal their own degradation over time. Certification tests become longer, harsher, and more representative of real-world operations. Yet, even with these changes, the fundamental lesson remains unresolved. Aviation is a balance between efficiency and robustness. Every kilogram saved improves performance and economics, but reduces structural reserve. Every layer of automation improves consistency, but alters how loads are applied. The stall sits at the intersection of these trade-offs, a reminder that there is always a price for optimization. In the silence after an accident, or in the uneasy calm of a grounded fleet, that reminder is impossible to ignore. The aircraft that once symbolized confidence is revealed as a system under constant negotiation with physics. Its safety is not guaranteed by design alone, but by continuous vigilance, humility, and adaptation. The catastrophic sequence is never just a moment. It is the visible endpoint of years of invisible processes, of microscopic failures accumulating under assumptions that seemed reasonable at the time. And when it unfolds, it does so with an indifference that is uniquely physical. The laws governing it are not moral or emotional. They are absolute. In that absoluteness lies the true danger of the stall. Not that it exists, but that it tempts engineers to believe it has been conquered. When that belief takes hold, the margin between flight and failure narrows quietly, until one day, without warning, it disappears entirely. The formal investigation always begins the same way, with silence. The aircraft is no longer a machine in motion, but a collection of fractured components laid out in a hangar, each piece tagged, photographed, and reduced to evidence. In this stillness, engineers search for order within destruction. They are not looking for drama. They are looking for causality. Every fracture surface, every deformed fastener, every delaminate composite ply is a sentence in a story written by physics long before the final flight. Microscopic analysis becomes the primary language of truth. Under scanning electron microscopes, fracture faces reveal their history with unforgiving honesty. Fatigue striations appear as parallel lines, each one representing a single load cycle, a single flight, a single moment when the structure was stressed but not yet broken. These striations march steadily across the material until they abruptly stop, replaced by the rough, chaotic texture of overload failure. This boundary is critical. It marks the exact moment when slow degradation transitioned into catastrophic collapse. Investigators trace these striations backward, like forensic archaeologists, toward their point of origin. Often, that origin is unremarkable: a rivet hole edge, a bonded joint termination, a subtle thickness change in the skin. Sometimes it is a manufacturing artifact, a tool mark, a microscopic void, a fiber waviness in a composite layup. None of these features violate specifications in isolation. None would alarm an inspector during routine checks. And yet, in combination with operational reality, they become lethal. Parallel to the material analysis, aerodynamicists reconstruct the final flight environment. They replay sensor data, control inputs, and atmospheric conditions. Computational fluid dynamics models are rerun with updated parameters, now informed by what actually happened rather than what was assumed. These simulations reveal flow separation patterns far more aggressive than predicted during certification. They show localized pressure peaks striking the wing skin in regions never identified as critical. The stall, it becomes clear, was not a single event. It was a regime, one that the aircraft entered repeatedly over its service life. Structural engineers overlay these aerodynamic findings with load histories. They calculate stress ranges at critical locations and compare them to original fatigue assumptions. The discrepancy is often stark. Components certified for a certain number of cycles were unknowingly subjected to far more damaging spectra. High angle of attack operations, once considered rare edge cases, had become routine. The structure did not fail prematurely. It failed exactly when physics said it would, given the loads it actually carried. This realization reframes responsibility. The failure is not the result of a single bad decision or a single flawed calculation. It is the product of systemic optimism. Design teams trusted that automation would prevent dangerous regimes. Certification authorities trusted that operational behavior would match assumptions. Operators trusted that compliance with procedures equaled safety. Each trust was reasonable. Together, they formed a gap, small enough to ignore, large enough to destroy an aircraft. The grounding of a fleet is the most visible consequence of this reckoning. Airlines cancel flights. Supply chains strain. Public confidence wavers. But within engineering circles, the impact is deeper. Entire design philosophies are put on trial. Weight-saving strategies are questioned. Load envelopes are redefined. The relationship between aerodynamic protection and structural exposure is scrutinized with new urgency. Regulatory responses follow, precise and uncompromising. Fatigue certification requirements expand to include high angle of attack load cases explicitly. Full-scale test articles are subjected to brutal regimes, cycling wings through repeated near-stall conditions while monitoring crack initiation and growth in real time. The goal is no longer just to prove that failure will not occur within a certain number of cycles, but to understand how it will begin, where it will concentrate, and how it can be detected before it becomes critical. Inspection philosophies evolve as well. Traditional interval-based inspections give way to condition-based monitoring. Strain sensors, fiber optic networks, and acoustic emission detectors are embedded into wings and fuselages, turning structures into continuous data sources. These systems do not wait for visible damage. They listen for changes in stiffness, for the acoustic signatures of crack growth, for the subtle shifts that indicate material degradation long before it becomes dangerous. Design changes are equally profound. Stress concentrations are treated as enemies, hunted and eliminated wherever possible. Window corners are rounded more generously. Fastener patterns are redesigned to distribute loads more evenly. Composite structures are engineered with fail-safe behavior, ensuring that damage progresses slowly and predictably rather than catastrophically. In some cases, designers accept additional weight as the cost of resilience, a deliberate retreat from the razor-thin margins of extreme optimization. Yet even as these lessons are absorbed, the stall remains a paradox. Aerodynamically, it is well understood. Structurally, it is increasingly well characterized. And still, it cannot be eliminated. It exists because lift has limits, because airflow separates, because materials fatigue. The only choice engineers have is how close they choose to operate to that boundary, and how honestly they account for its consequences. This is where the concept of hubris returns, stripped of accusation and reduced to its essence. Hubris in engineering is not recklessness. It is the quiet belief that past success guarantees future safety. It is the temptation to trust models over experience, simulations over scars. Aviation history shows repeatedly that progress accelerates this temptation. Each new generation of aircraft is safer than the last, until it encounters a failure mode the last generation never revealed. The stall has played this role before. In early aviation, it taught pilots respect for angle of attack. In the jet age, it taught designers the importance of training and warning systems. In the era of automation and advanced materials, it now teaches something subtler and more unsettling: that protecting the pilot does not automatically protect the structure, that removing human variability can concentrate mechanical damage, that safety is not additive, it is interactive. For engineers, this lesson reshapes priorities. The question is no longer, can the aircraft avoid a stall? But what does repeated proximity to stall do to the structure over time? It is no longer enough to certify behavior at the boundary. Survivability near the boundary must be proven. This shift does not make aircraft weaker. It makes them more honest. In the final pages of an investigation report, conclusions are written in measured language. Probable cause is identified. Contributing factors are listed. Recommendations are issued. But beneath this formal closure lies an unspoken understanding shared by everyone who reads it. This accident, this failure, was not an anomaly. It was a reminder that flight is a negotiation with invisible forces, that every takeoff consumes a fraction of structural life, that every efficiency gain trades one risk for another, and that the most dangerous failures are not those caused by ignorance, but those born of confidence. When the aircraft returns to service, modified, reinforced, recertified, it once again appears flawless. Passengers board without hesitation. Wings flex gently against the sky. The stall remains distant, managed, controlled. But somewhere within the structure, the memory of failure persists, encoded not just in metal and composite, but in new rules, new tests, and new caution. This is the true legacy of stall-related structural failures. Not fear, but humility. Not paralysis, but restraint. They remind the industry that engineering excellence is not defined by how close one dares to push limits, but by how carefully one respects them. Because in aviation, the margin between mastery and disaster is never erased, only managed. And the stall, silent and patient, waits at that margin, indifferent to ambition, unmoved by confidence, enforcing the laws that no amount of ingenuity can repeal. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault,